can start the session.
Right. So let me start with PCA. I really like the slides I made. Where do you go to? Can you guys see it?
Mm-hmm.
Nice.
But you sound a little bit distant, a little bit.
Oh.
Oh, much better.
Okay, nice. Can you guys hear me now?
Yes.
Yes.
Okay. So PCA. So first, not PCA, dimensionality reduction. Uh-oh. Why is it not going?
Oh, you probably have something in front of your, like an alert or something.
Yeah. No, it's working now. Yes.
What? Look at you.
Yes.
But you had the most time to prepare for this, so.
Yes. So far we've talked about classifiers, linear regressions, support vector machines, decision trees, random forests, and all the other fun stuff. And these are all examples of sort of like supervised learning algorithms. Now in supervised learning algorithms, we give the model samples and a label. Like for example, we gave the first one we learned, we gave the model sort of like features with the houses, and then we gave them prices, and we're like, okay, this is a new house. Help us predict the price for this one. Or in the other one where we're predicting, we gave the model images as well. And then we're like, okay, help us predict what the handwriting, we gave the model handwriting images, and we're like, help us predict what number we're trying to get here. So all of these are examples of supervised learning. The next one is actually unsupervised learning. And this is more along the lines of like, it's neither, this is a very simple definition I got for unsupervised learning, is training a model using data that is neither classified or labeled. So unlike before, where we give it something that we want to predict, we just sort of like say, try and, what can I get from this data? What can you help me get from this data, essentially? So if you can see, just look at the figures, the cartoon below, it's sort of like, the one to the left is supervised learning, where basically we give it an image and then we ask it to predict what the image is. Versus in unsupervised learning, you see it's sort of like sorting. You just give the model all the data, and basically it sort of sorts it out for you and says, oh, this looks like this looks like this looks like this, and this looks like this. Now, there are common use cases: dimensionality reduction, clustering, anomaly detection, autoencoders, and association. We won't cover everything, but I think for today, the main one was dimensionality reduction. Yes. So the curse of dimensionality, and basically our motivation for doing this. So the very first one is basically, if we have a lot of features, it becomes very hard to visualize. Like for instance, if this is, for example, say this is your original data set, right? And I give you size and I give you rooms, and I want to see how both of them are correlated. You can easily do something like this. You can plug them both like this. And if I add something like, okay, this is the size of the house, these are the number of rooms, this is the number of schools around the district, you can plot something like this. This is supposed to be 3-dimensional. I don't know if you can tell from my drawing, but yes. But if you add any other feature, it becomes sort of difficult to visualize the fourth dimension. And I learned last night, I think it was basically the fourth dimension is technically time or something. But it just basically becomes very difficult to visualize. And another thing is also the predictions are much less reliable in higher dimensions than in lower dimensions. And one way to offset this would be to get more training examples, so put up more examples. But this becomes very, very expensive because the number of training examples needed to offset it increases exponentially, this part here. So basically what we need to do is to reduce the number of dimensions. Yeah. Also, it makes computation much faster as well. Like just generally, the less data you have, the faster it'll go. There are two main approaches to dimensionality. The first one is projection. The second one is manifolding. So I want to start with the projection one. So first we project every training instance perpendicular onto this substance in the first image on the left. So basically, this is X1, this is X2, right? This is our original, the blue here is our original, sorry, not the blue. The clear ones are our original data set. Like these are our original data set, like these ones. No, I didn't plug that part away. Like these ones, these ones are sort of like the white things are our original data set, like the core ones that we gave you. And then basically we draw a line here, this green line, and we project sort of like, I don't know if you can see it well, we sort of like say, project this one back onto the, what do you call it, onto this line. So rather than have the original data set, which is in this one, right? Which is using two axes, we'll use one axis now. We'll just use this green axis and sort of make it sort of like a number between them. At this point here represents the origin, right? This green point represents the origin, and then you can go back or forward. Similarly, if I give you something 3 dimensions, you can reduce it to 2 if you project it onto sort of like a 2-dimensional plane. Yes.
Mm-hmm. Yeah, and I think we went through a little bit of this, and welcome Nazanin, I hope you're good. So we went through a little bit of this with the, remember the polynomials, right? Mm-hmm. Because everything, if you can normalize it and becomes a linear representation. So for example, like linear classification or linear regression, then it's easy to predict and it's easy to interpret. But so when you have sort of like what you're saying, multiple differentiations and multiple like multiple dimensions, then you always have to figure out how you're going to represent this back to a place where we can apply a mathematical function, right?
Mm-hmm. Yes. So basically, yes. In the first case, this one, we've gone from 2 dimensions to 1 dimension. And the second one, we've gone from 3 dimensions to 2 dimensions. Mm-hmm. Yes. Now, but projection obviously doesn't always work. In some cases, like if you want to project something like this, like let's say it's very difficult to project something like this. Like if the data is just like this, it will be very hard. They try to project it here. And it didn't work. Okay, then this is the second way that they do dimensionality reduction. Now, if you look at this one, if let's say we have a plane, like a 2-dimensional plane, or just basically sort of like a flat sheet that goes like this, which is also 2D, that goes like this, we will get a very, very good, representation of data. That's sort of like what manifold learning is. So this is the definition I took from the book. A D-dimensional manifold is part of an n-dimensional space that if it locally resembles a 3-dimensional hyperplane. Like in the case of this one, we went from 3, our original, which is n, we went from 3 to 2. Yes. It makes 2 main assumptions. The first is that most real-world high-dimensional data set lie close to a much lower dimensional manifold. Basically, it's saying that this is possible. Like it's possible to do that. And then the second one is that the tasks like classification or regression will be simpler. We'll talk more about this one, I think, in the next slide. Yes, so this assumption does not always hold. So this is basically the second assumption. Like if we fold it like this, if we go like that, like the Swiss roll, unroll it sort of like, unroll the Swiss roll, you get something like this, right? Versus if you do this one you can see that it's not as clear, it's not as like, the data set is not as split. Yeah, the decision boundary is not always easy to get sometimes. But yeah, so the next one right now is PCA. PCA, Principal Component Axis. It uses the projection method. Remember, we talked about 2. We talked about projection and we talked about manifold. This one uses the projection method. It identifies a hyperplane that lies closest to data, and then basically it picks the hyperplane or the new plane that will most likely lose, that is least likely to lose information. Yes. If you look at this graph, I was so happy when I saw this plot because it was difficult to get something like this. But if you look at this graph, like if you see the line, we want two things. We want our new plane to do two things. Either the highest variance, right? Which means it's not losing any much, which means it retains a lot of data. It retains a lot of the original data. And two, the reconstruction error. So reconstruction error is something we'll talk about too later on. And reconstruction is basically like, say we're going from this green line back to the blue one, right? We should try and get it as close as possible to that one, right? So basically this is just sort of like a GIF showing, you'll see when there's a red dot, there'll be a red dot when at the peak one, I believe. I think it's this one. No, yeah. This is what it is. Yes. So far, how is it? Is it confusing? Is it like, does any part need clarity? Or?
Sina Nazanin, does that make sense?
It does for the most part, but I think it will make more sense as you keep going. But yeah, but we can discuss it later as you go a little bit deeper into the topic. Yeah, thanks.
Yes, it's okay.
Yes. So basically with PCA, we need two things, like it's in the name, principal components. So the first thing we need to get is the principal components. Now, principal components are sort of like the unit vectors where the new dimensions are. Yeah, basically the new, what do you call it? The unit vectors that make up the new hyperspace. And there's two ways we can get it. Like before, we've always done something like this. We use the NumPy method, or we use skitlearn. Now, you basically get the principal component access from this thing, singular value decomposition. Yes, singular value decomposition. And you can do it, basically, this is using NumPy library to do that. And you can see being called here on the original data, on X-centered data. Now, what it does is it'll give you this entire thing, right? It'll give you n components, right? If you want, if you want a
you have an exam tomorrow?
Yes. If you want a, if you want a one-dimensional hyperplane, then you only pick the first one. If you want a two-dimensional hyperplane, you pick, that's like a normal flat plane. The first one is if you want a line, you just pick one of these ones. If you want two, you pick if you want like a plane, because a plane is made from two, from two vectors. So you make those two, you pick two. And similarly, if you want three, you'll do the same thing. You'll do like three vectors from there. And basically this X2, that's what they try to show in this line of code here in the book. And then basically, yeah, to get the projection, you just multiply your X by those VTs. But I can't remember what it's called. Let me see. I think it's called, yeah. Oh, I just think it's just principal components matrix. Okay, that makes sense. Yes. Does that part make sense? That was the part I always broke down.
So I think that probably part is more important for you and Nazanin, right? Because you guys need to be able to code from scratch, right? But what I would say is that, you know, Sina, me and you just need to know when do I use my PCA? Dimensionality is super important. So if you think about the trauma database, right? So if you went through the NTDB channel, we see this is a big, and this is a paper that we'll all review because it goes through all these basic components. You have all these, let's say you have 1,000 medications, right? Those cannot fit into your model. You need to figure out what model you're gonna use, right? And so I would say that I actually prefer, to be honest, I'm not saying that it's not a way to do, I like this, but when I see this, what I emphasize more on is to say, you know, this is the most important, because if you're using the library, you're just trying to figure out how to call this. Now for you and Nazanin, and I don't think that this book club will help you get there, is that, you know, you just have to know, okay, I need to be able to code something like this from scratch, which is all I do is provide you more resources to try and help you do that.
Thank you.
Okay.
Yes. And then the other thing, so originally in these ones, we're just like, okay, we have 3 dimensions. We have 3 dimensions, we'll go with 2. We have 2 dimensions, let's reduce it to 1. But actually, we don't really know how well, basically you want to be, like, if I give you a good data set, you want to be able to say, okay, these are a good number of dimensions I want to reduce it to. And this is where I won't lose most of my original data, right? That's what part of choosing the number of dimensions. There are 2 ways you can do it. You can just use sort of like PCA, which is this was awesome because I did this from scratch. I did this from scratch for one of my homework. And I didn't know, but this is nice. Like this one is nice. And then also something like this. Yes. These are basically, this one is the nicer one. I like this.
So anyway, what you're trying to say, I didn't catch that part for the home assignment, but the scratch assignment, but you're saying that this PCA, you know, maps, you know, transforms everything, right? But looks for where there's maximum variance because it wants to include everything, right? Because in the dimensionality, but this is how it draws that curve and ends up like where it feels like it's the peak of the curve, right?
Yep.
Is that?
So basically originally you get all of this, VT, you get VT. And let's say you give it 4 dimensions, like your original data set has 4 dimensions. VT will have 4 principal components, right?
Okay.
And then what you want is basically you want to pick the number of dimensions, like either it can be 1, it can be 2, it can be 3. Like say your goal is not to visualize the data, right? You just want to reduce the number of original dimensions. Then what you can do is basically with each, after each, when it compares, when it plots the data, when it reduces the data on each dimension, there's a certain number of percentage of the original data that is still retained. That's what we get from the variance. So basically we're trying to say, okay, don't let that variance go beyond 95%. I still want to somewhat be able to get 95% of sort of like my original data from my projections back.
Okay.
Yeah. You use the elbow method. This is one way. This is the nice way to do it. You could also use sort of like the elbow method. We've talked about this one with, I think, picking the value of K in, oh, no, we haven't yet. No. Sorry, we haven't yet. Yes. This is another thing. Yeah, this is basically where he starts talking about the variance. And basically you can, once you reduce it, it's possible to get back the original data set, but note that it won't be exactly the same. Like he gives the instance of this one where basically this is the original handwriting. They did PCA, they got this, and they did PCA out of this, and then they got this when they tried to project it back. So they got this is the original, they did the PCA, then they tried to get it back. Yeah, this is not the PCA dimension. That's not the PCA one. Yes. And then PCA starts getting more interesting because it starts looking more like the ones we've tackled before, like their stochastic gradient. They're sort of like stochastic, sort of like the stochastic gradient descent with PCA. There's also, there's kernel PCA, then there's also mini batch gradient. I said mini batch gradient descent. There's like gradient PCA in batches as well, which I thought was interesting. The first one was the randomized Pca, and basically just uses sort of like the stochastic algorithm like we use in stochastic gradient descent when we're doing, which one are we doing? In our, I think, regression one, in our regression or classification one, we're using stochastic gradient descent. This is the mini batch version of Pca as well. It uses similar techniques to mini batch gradient descent. Sort of like, this is sort of like for epochs, for X and epoch and all that. This is sort of like where it's marking that what do you call it? That code as well. Now, once again, this is very useful for like how we were in mini batch gradient descent. If you're training very huge amounts of data, it helps you get something quickly, or if the PCA is online. Those are very useful tools for those ones. And then finally, yeah, no, this is not finally. This is the last side of PCA, and basically employs similar techniques to the kernel in SVM. I think this is the point. Oh, no. Yes. Okay. So basically, the author talks about picking kernels. Let me see. Yes, this is where we are. So basically, you can pick either like a linear kernel, your RBF kernel, or your sigmoid kernel. Each of them will give you different, what do you call it? Different projections. And what the author said was like, there's two ways you can pick. You can basically select a kernel and a hyperparameter tuning. So the first one is we can use grid search. I think we use grid search with random forest trees.
Yeah, anything, right?
Yeah.
Pretty much anything that you need. Remember, much as people present their work and say, and you know, someone like Nazanin, who's been coding a lot this year, may have already her pipelines and things that she's set up, right? Which is what you're doing now with Chima, right? You're starting from scratch and you're starting to work with medical imaging data that you haven't worked with. But once you set this thing up, remember from the very first chapter of this book, it says that your eye can figure out what the pattern is, but if it's machine learning, you're trying and trying many times, and then evaluating, listing, and deciding what's my best result. So if you think about something like the NTDB work we did, you can see that we tried like XGBoost, all these algorithms, because the truth is maybe from reading a paper or something else, which is why there's always this rush to beat the state of the art, you really cannot tell that this is the correct model to use on this data set. That's just not known.
I see. You have to try. Yes. So basically, sort of like with grid search, these two, imagine these two are axes on a grid. This is one axis on a grid. These ones are another axis on a grid. And then basically, you have this, you have that. And then you're running PCA on all of them and checking which one gets you the best original. Actually, no, they put it back. They basically ran linear regression, logistic regression. And we're trying to see which one gave the best logistic regression value. Yeah. Which one gave the best logistic regression value? Yes, that's one method. The other method is basically just rather than use the logistic regression here, like they used here, you could also just look for the one that gets you the least, that has the lowest reconstruction error. Remember, reconstruction error is when you do PCA, and then when you give it back, basically how different is the original from the basically undone PCA. Yeah, how different are those two? Those are sort of like the two methods that they try to use in this one. And yeah, and this is the last one. So far, all the other stuff we've talked about, we're using, what do you call it, projection. This one is different in that it uses basically manifold technique. And basically it's actually quite interesting because let me see if I got it this time. So what it does is, imagine, not this image, let me use the original image. Yes. What it does is, like, it'll pick a point like this. Like, here we have one point here. It'll pick one of these points. It'll pick a point like this. It'll basically try to map that point and its neighbors and its closest neighbors onto a lesser dimension, such that the distance between this point, like this point, and its neighbors are the same, or somewhat identical. Like, basically, if we have, I couldn't find like a good visual for that one, but let's see if, yes, that's basically what it's trying to do. Is basically it'll find a point like this, then it will say, okay, these ones are its neighbors, and then it'll plot all of those on sort of like a lower dimension. Did the explanation help? Did it make sense?
Mm-hmm.
Yes. Okay. That was mainly it. And yes, this was sort of like the math behind it, which I was like, yeah. And oh yeah, I didn't like the math, but we can do that one after. But yeah, after, then he talks about other dimensionality reduction techniques. And the first one was this one, which reduces dimensionality while trying to preserve isomap, and then T-distribution, stochastic neighbor embedding, linear discriminant analysis. Yeah. Basically, there's a lot, he's basically trying to say that there's a lot more than PCA and, because I personally didn't know any other one besides PCA at first. Mm-hmm. PCA and LLE. So, and all of this are in the skit-learn library that you can use. Skit-learn library. Yes. Was there any part that maybe I didn't cover too well? What would you like to see more?
So I think for me, what I think is that as someone who's starting to get into this space where we are going more towards the traditional machine learning techniques, is that I'm trying to see what these guys end up doing on this, because I didn't listen to, I think it's Sebastian or something. And for our talk here, because I think, you know, dimensionality is a big problem. I mean, Nazanin, don't you agree that when we have all these calls with Imon, this is what we're always talking about? Like, how did you reduce your dimensions? I felt like maybe this is too simplistic, and I'm not so sure it's maybe because my ignorance, I don't understand it, or there's something else, you know?
Yes, it's really important in machine learning. And also when we use dimensionality reduction, we can speed the running of the code.
Yeah. So, I mean, I thought I posted that link on the chat, the YouTube for, I think it's Sebastian who teaches this.
Might be on the slide.
The one who's teaching the live course, right now.
Might be on, I think it should be on the slide.
Just wondering, like, if, because I expected